Okay, great. We are glad to have Ariel Ashkenazy with us, visiting from Bar Ilan University. He works in Eli Cohen's group. And so give a little bit of background. Ariel did a dual undergraduate in electrical engineering and physics, but he considers himself a physicist. And went into electrical engineering and started. Are you doing a PhD in physics or in electrical engineering?
Technology.
So it is electrical engineering, but you're still doing physics.
Yeah.
Okay.
Because I'm in Ali's group.
Yes. And he's actually getting close to finishing his PhD, and hopefully we can convince him to come here to Chapman in a year or so. Anyway, he's going to talk about us about two very nice results on number splitting and also some speckle imaging. So turn the time over to you, Ariel.
Thank you, John. I'd like to first thank the organizers for having me, and special thank you, John, for having me in your lab for the last 10 days or so. It was a very, very nice experience, and I've met brilliant people and have amazing discussions. And overall, it was a very nice experience. So thank you. As John said, we talk about photon number splitting, which is an attack on quantum key distribution systems. Proposal of experimental implementation of this attack. And perhaps I hope we'll have some time to also discuss super resolution using speckle illumination, which is computation free. First, some acknowledgements to the people I've been working with. Professor Wolf Fixler and Professor Eli Cohen are my co-supervisors of the PhD. I also work with Professor Zev Zelevsky, the Dean of our faculty, Professor Barak Dayan from the Weizmann Institute on the quantum key distribution research, and Professor Andrei Stefanov on the super resolution. Andrei is from the University of Bern in Switzerland. Okay, so let us begin with the first topic, photon number splitting attack in quantum key distribution systems. Brief introduction. Quantum key distribution originated in 1984 with famous BB84 Bennett and Brassard protocol, which is supposed to give you a provably secure way of communication. And arguably, quantum key distribution systems are one of the most advanced quantum technologies today. There are already commercially available products of quantum key distribution systems. QKD. We will use the BB84 protocol, time-encoded BB84, as a benchmark to our analysis. So let's all remind ourselves of this protocol. We have four basis states. Z basis, we have, we have time bin encoded, which means that you have two temporal bins, early and late. And if we have the photon in the early time bin, then we will say this is the zero state, the Z basis zero state. And if the photon is in the late time bin, this will be the one state. And for the X basis states, we have the plus and minus superposition of these states. And the protocol is as follows. Alice randomly chooses a state and communicate it to Bob. Bob measures the qubit in a random basis. And after they complete this quantum communication, they will publicly announce the basis that they have used, and they will discard all of the bits that were obtained with different bases. And so they will end up with a sifted key. And then they will take a portion of that sifted key and we look for any discrepancies in the bit values that they obtained. Assuming that everything is perfect, they will expect perfect agreement between the bit values that Alice sent and what Bob measured. If Eve tries to eavesdrop on the communication, basically what she can do is intercept resend. So just intercept the communication, measure, and then resend according to what she got in her measurement. Because she doesn't know in what basis to measure, she will introduce quantum bit error rate or Q-bar, which is 25%. And that will be detectable in Alice and Bob check. And if they see that they get such high Q-bar, they will get rid of the communication and start over. That was the idea in 1984, and that is provably secure. Everything works perfectly fine, but you assume that you are using a single photon source. And single photon sources are not so simple. So basically what usually is done, we are not using single photon sources, but instead we are using attenuated laser pulses or weak coherent states. Basically a coherent state, which is a superposition of number states. And the mean number of the photons is below 1. So it mimics a single photon for that purpose, for the purpose of QKD. A coherent state we will denote with alpha, which is a complex number, and mu will be defined as the absolute value squared of alpha, and it gives you the mean photon number in that coherent state. So if we're using weak coherent state for our communication, for our time being encoded QKD, the states, the Z basis and X basis states will look, as you can see here in the table. So having a coherent state alpha in the early time being or the late time being will be the 0 and 1 states in the Z basis. And for the X basis, you don't get cat states, okay, superpositions of coherent state. What you get is just a coherent state in both the early and late time beings, but with a phase plus or minus phase. That will be the X basis states. And it works. However, as you can see in that communication between Alice to Bob, once we move to use weak coherent states, we no longer have a single photon in each qubit that we send. We might have more photons because a coherent state is a superposition of different number states, and you can have, with non-negligible probability, more than a single photon. You can also have vacuum, of course. And that has been known for years to open the way for a vulnerability, for an attack called Photon-number-splitting. Basically, what the theoretical attack says is that Eve will perform quantum non-demolition measurements on each qubit, on each pulse that is communicated. And if there is vacuum or a single photon in that pulse, then she does nothing. If there are more than a single photon in that pulse, she will split this pulse and send one photon to Bob, and the rest of the photons she will keep in a quantum memory in her side. She will wait until the end of the communication where Alice and Bob publicly announce their bases, and then she will measure the photons that she were able to extract. She will measure them in the correct basis and get full information from all of these multi-photon pulses. So theoretically, that's an amazing attack. She introduces no Q-bar. Bob keeps getting a single photon, and from his side, everything works perfectly fine, but she managed to get all of the information from all of the multi-photon pulses. So why Eve is still upset in this picture? Basically, because the greatest researchers in this field claimed for years that this attack is interesting theoretically, but it cannot be implemented, maybe even unphysical. Why? Because you have to perform quantum non-demolition measurements, which are really difficult. Then once you perform the quantum non-demolition measurement, you have to somehow split the pulse deterministically such that one photon goes to Bob and the rest are kept at your side. Then you need to have a quantum memory. And all of these parts are really, really difficult experimentally, perhaps even impossible. We beg to differ. And we propose an implementation that is based on sprint mechanism. Sprint is short for single-photon Raman interaction. This is a mechanism that was demonstrated experimentally, that is well studied theoretically. You can see this paper from 2015, but it goes back way before, and many more works since 2015, as you can see. And this mechanism is based on a system that is a three-level system in a lambda configuration. You have two degenerate ground states and one excited state. And then you have the transition from one of the ground state to the excited state coupled to one direction in an optical fiber, and the other transition coupled to the other direction. Okay, so if you have photon coming from one direction in your optical fiber, it will interact with one transition, and it will have destructive interference with the emitted photon from the atom, such that it will be reflected while changing the state of the atom. So I will not go too deep into the details of physics of sprint. That is not the purpose of our research. But for our purposes, we can think of sprint as an optical switch. Basically, you have a pulse with n photons incident on the atom. One photon interacts with the atom and is reflected. And while doing so, it changes the state of the atom such that the rest of the photons are transmitted with no effect from the atom until you have some pulse propagating in the other direction and doing the opposite interaction. Okay, so basically a single photon extractor. And it was demonstrated, it's a technological capability that we have today. So the idea for the attack is as follows. Eve has a sprint atom. She places her sprint atom on the communication channel. And before the communication of each qubit, she resets the atom to be reflecting for the direction of the communication. Alice sends her pulse. If the pulse contains vacuum or single photon, then it is reflected and directed to Bob. But if there are more than a single photon in that pulse, then one photon is reflected to Bob, but the rest of the photons are transmitted. And if quantum memory is placed on the transmitted arm, she gathers all of these multiphoton extracted photons from the multiphoton pulses. She waits until the end of communication and measures in the correct basis. So basically, instead of performing the task of quantum non-demolition measurement and then the splitting, the atom does it all for you in a single step. It just decides if there are more than a single photon. If there are more than one, you get all of the extra photons.
Eve doesn't seem very dangerous here.
These are the most dangerous people.
So just a quick question for you. What is is that just some resonator? What is the physical mechanism? It looks like you're just drawn like a ring cavity?
Yes,
or-
you have whispering gallium modes in cavity, and one propagation is allowed only for a single polarization. That polarization is coupled to a single transition in the atom.
Oh, so there's an atom on, there's like a defect on the, or an atom?
An atom nearby, they are sending atoms nearby the cavity.
I
Okay, so
see.
it moves like a cloud of atoms near
Okay. They're
the
doing
cavity,
one,
and then
one by one.
approximately one by one. On
Okay.
average, you have one. Yeah.
Okay, so if you had more atoms by there, then you would get more photons in doing this.
Yes, but
So
the
discrete-
probability is low.
Okay.
The basic idea is that, at least theoretically, you can have single atom near your cavity interacting only with one direction and with the other.
Why not just use a defect or something like that, like where there's a single transition rather than, so basically you're getting your discreteness in your photon number from your atomic discreteness in your,
Yeah.
because you only have a single atom, but you can also get it from like defects in.
Yeah, but then the rest of the pulses that I will send, if the atom already relaxed to the ground state, it will interact again with the pulse. Right? You want to have a transition that is irreversible. You have a transition to the excited state, but then you relax to a different state that is not coupled to that direction. So now it becomes transparent to your photons.
I see. But you can
But
always,
there are works on.
you can just go back. I mean, you can do the inverse.
It will depend on the temporal window that you have. If you have a relaxation, then it's a problem because you have again the interaction. Yeah.
Okay, so you're matching your mode very closely to your resonance of your.
Yes. That's not my work. That's
Okay.
Barak Dayan's.
So any reasonable person doing cryptography would say, well, let's just make sure we don't do it at this atomic resonance.
Yes. Also, I would say that's an excellent point. So you're saying the exact implementation will have an effect of whether you can perform this attack or not.
Yes.
I will say even more. If you wouldn't use time bin encoded, but polarization encoded, then the attack will not work because single polarization is allowed only in one direction, and the other direction is allowed on the opposite polarization. So if you have like a superposition of polarization, placing this print will just destroy the coherence and it will be detectable. So it works for time bin encoding.
But you can
And
always change time to polarization.
you can do mathematically, you can do. There is a complete equivalent. If you're using mutually unbiased states, it doesn't matter if you implement it in time or polarization or frequency or whatever. But when you talk about the physical realization, it does depend, because here in this system, polarization will be detected. If you have polarization encoding, it will be detected. It will just destroy the communication. But if you have time encoded, and that is what most quantum key distribution systems are using today, then that will work. Again, given that you have the exact mode and everything.
So Bob could also do statistics on his incoming particles and determine.
So we're now moving to the analysis. So this is the idea, and we gave a mathematical description of the system and then performed the analysis, obtaining analytical expression for all of the detection probabilities in that scheme. And we have an assumption. And our assumption is that Bob doesn't have photon number resolving detectors. This is an assumption that, first of all, is reasonable. It is not used in quantum key distribution systems today. They just have a click or not detectors. And moreover, we assume that the communication between Alice and Bob was perfect. Without Eve, everything works perfectly fine, no losses. The detectors are perfect, no dark currents, no dead time, nothing. So basically, Alice and Bob are doing everything perfectly fine. They are implementing QKD as best as they could. Eve comes with her spirit atom and attack the communication, and we want to see what happens. If they have photon number resolving detectors, then basically this attack will not work. But again, systems today are not using. It's much more complicated to have such detectors. Okay, so as you can see, the equations are not so fun to work with. If you're interested in the entire analysis, you have our paper in Advanced Quantum Technologies. Supplementary is extremely interesting. So let's just talk about the results. And the first question is, okay, does it work? Can Eve actually get information from the multi-photon pulses? And the answer is yes. So basically, if you look at the Z-basis states, you will get perfect detection at Eve's side. So whenever she gets a photon, meaning whenever there is a multi-photon pulse, she will get a correct detection in the Z-basis. In the X-basis states, it's not perfect, but as you can see here, it's higher than 85%. So there is some incoherence due to the interaction with the atom that will not allow her to get perfect detection for the X-basis states, but still she gets high detection, high ratio of correct detections. And if we combine the X-basis states and Z-basis states, so we have more than 92% correct detections for the multi-photon pulses. And as mu increases, you see that this ratio increases asymptotically to 1.
What is a typical mu for these?
So it will be below 1, probably 0.1. Yeah. But we were interested in, first of all, to see the asymptotic behavior, that it really behaves as we think it should, but also more advanced protocols like the decoy state, which we've already talked about, are using different mu's. So they have higher mu numbers. And we wanted to see exactly what we get for each mu. Although we haven't analyzed decoy state yet. Right.
Silly question. What does it mean that you're getting correct detections with 0 mean photon number?
Okay, so the probability of getting a photon is actually 0. And that will be the next slide. So here you see, if she gets a photon, what will, and she measures it, will she get a correct detection?
So it's like a singular edge case. Okay.
Yeah. So
I noticed
the
that's-
0 here is not exactly 0. In the simulation, it's 0 point whatever.
Okay.
Yeah.
I noticed that's about 85.3%. Is that,
Where does it come from?
well, that is the ratio of
Okay, so it's,
perfect cloner, universal cloner if you're restricted to the greater circle.
really,
85.3%.
that's an excellent comment. Okay, so just a second, let's talk. So here we see if you get a photon, what will be the ratio of correct detections? But now we look at photon number state. So if I have 0 photons in my pulse, or 1 or 2 or 3, what will be the ratio of correct detections? And that can give you much more intuition on the result. So you see that if the pulse is vacuum, okay, so basically you don't get any detection. If there is a single photon, it goes to Bob, it doesn't get anything. But if you have 2 or more, then you get 85% correct detections or higher. And in that analysis, we have the analytical expressions for the ratio of correct detections. and as a function of n, and that can be very interesting to look at because we've asked, I forgot his name. I think he also works in Japan or part of the quantum institution here. And he had some ideas where the expressions are coming from, but it wasn't very fruitful. Your comment might be very interesting. We should talk about it. And we also have some work on optimal cloning and weak measurements as an attack. And there are some similarities. We really should look into it. Okay, so basically what we see is that as the number of photons increases, the ratio of correct detection increases, and that is expected because the single photon that was reflected to Bob has very negligible effect on the state that eaves get when the number of photons is very high. Okay, but for n equal 2, we get the lowest ratio of correct detections, and it's above 85%. So Eve is very pleased with that result. We can also think of the information gain. This is what you were asking. Okay, so you assume that she gets some photons, and then you ask what is the ratio of correct detection. But what if we also take into account that for low mu, the probability of obtaining more than a single photon is very low? So here you see the information gain, which is basically whenever Eve gets a detection, that will be her bit value. When she doesn't get a detection, she just flips a coin and randomly assign a bit value. And what will be the ratio of correct bits in Eve's string as compared to what Alice sent? And you see that for mu approaching 0, then the ratio is 50%. She gets no detection, so she just flip a coin and she gets 50% of the bits correct. But as mu increases, she gets higher and higher, and asymptotically, it will get to 1 for very high mu numbers. And you can see the theoretical limit in red, and our attack is approaching that limit and has the same behavior, but there is some discrepancy, again, due to some incoherence because of the entanglement with the atom. And I would say that here we assume that if...
Would you call this information gain?
That's what we have used, but okay, if you have...
Because you haven't really gained any information if the probability, I mean, if it's random.
Yeah, so we can also look at the certainty in each bit that she has, like looking only at the bits that she knows she got a detection for. So we will get some different graph, but the idea is basically the same. She gets some information, and I mean, it's better than nothing, right? She gets.
How are you defining the information gain?
So again, for whenever she gets a detection, I have the probability of getting a detection, which is the probability of having more than a single photon in the pulse. Then I have the detection probabilities that I've calculated in my analysis. And whenever there's a single photon, then I just assume 50% correct.
Okay, so this isn't like an entropy calculation. This is
like
multiplying two probabilities.
Yeah. Basically, just
probability. But you don't know that it's correct.
What do you mean?
When it's because if
we'll know, if she gets a detection, great. She doesn't get a detection, okay, she knows that it's a random bit value.
If it's, maybe I'm misunderstanding, but if it's a random outcome, right?
No, she has a quantum memory. So she measures only after the bases were announced, and she performs the measurements in the correct basis. So whenever she gets a detection, that is the correct bit value.
I see.
Up to the 85%
I see.
ratio.
So this is the fraction of bits that she collects that are correct.
No, we also add the 50% probability of getting the correct value, even though it's just a random guess. But we can look only at certain bits. That will be a different graph, but again, you will get the same behavior. we get some theoretical limit, and we are slightly below. I would say that here we assume that Eve has a quantum memory. We also perform the analysis assuming that Eve doesn't have a quantum memory. In that case, she will just measure in the Z basis, right? Because for the Z basis, she gets perfect detections, and for the X basis, she does not. And in that case, we saturate the theoretical limit. So basically, it works. However, not only we have this slight difference between our results and
You
the
should
theoretical limit.
probably randomize your basis, your measurement basis. Otherwise, there's a preferential.
Okay, so one more assumption in the analysis is that Eve has perfect knowledge of the protocol that Alice and Bob are using.
Yeah.
So if they will use 0.6 for X basis and 0.4 for Z basis, we'll just change the basis of her atom such that X basis states look like Z basis. Okay, and then she will get higher information because she has more Z basis states. Follow. She
Well,
can have
I'm
she can
just saying you
transform
want-
X basis states into Z basis, right?
Okay, but you wouldn't want to just stick to your X. Well, you wouldn't want to just stick to one basis if you don't know.
Me as
If you
Eve,
have a quantum memory, yeah.
no, you don't want, because the perfect protocol for Alice and Bob, the best they can do is having 50-50. Because if they have a higher probability for one of the bases, then Eve will measure such that that basis gives her the correct detection. That will be like the Z basis states that we have, and the other will be the 85%. So she will get higher information if you have this unbalanced basis.
Yeah.
So
I'm not,
50-50 will be the perfect
Yeah.
for.
that's not what I'm saying.
Oh, okay.
No, you have a lot to cover. I'll talk to you about it.
Okay, no problem. Okay, so not only we see this difference between our results and the theoretical limit in the information gain, but we also see some quantum bit error rate. Again, in the theoretical works on photon-number splitting, it was assumed that no QBER is introduced. Bob gets perfect detections, everything works fine. But again, due to that entanglement with the atom, some of the coherence is destroyed, and Bob does get quantum bit error rate. You see that asymptotically it approaches the 25% like intercept percent, okay? But it is much below that number for reasonable mu. So there is some QBER, it is detectable. Usually it's assumed that if you are below 11% QBER, the communication is okay, taking into account all imperfections. So up to mu equals 2 or even higher, Eve is in the okay zone. And you can also see as a function of n, again, the QBER increases as n increases because you have a coherent state with many photons and Bob gets only one photon. So the remaining of the coherence that he has in his single photon decreases as the number of regional photons increases. Okay, some more additional points. Again, the paper has all the analytical expressions and we can play with it as we want. We also investigated the COW protocol, coherent one-way protocol. Basically, in this protocol, the phase is measured not only between the early and late time bins of the current qubit, but also between the late time bin and early time bin of the next qubit. And since Eve has to reset her atom before each qubit, she basically tracing over the atom, and that completely destroys the coherence. and that will be detectable. The photon number splitting attack for cow will look like intercept percent with 25% Q-bar. That will be detectable. So this cow is kosher. And experimental realization of this attack is currently undergoing in Berkeley and Slavit Weizmann Institute. Of course, when you go to experiment that, then you have much more things to worry about. And we have some preliminary results that you can see on the right, but we're still working on it. So that's it for this part of photon number splitting. Should we go to say some words
Yeah,
on super resolution?
yeah, go ahead.
Let's do that. Okay, so this is like a completely different topic, although it is a coherent part of my PhD thesis. So these topics are somehow related, but for the context that I will be presenting here, they are completely unrelated. And what we are doing here is to show how we can have computation-free super resolution method utilizing speckle illumination. So you know that the spatial resolution of an imaging system is limited by the numerical aperture of that imaging system. And there are many super resolution methods that were investigated in the past. Perhaps the most famous one is structured illumination microscopy. Like you see below, you have some structured illumination illuminating your object, and then you perform some post-processing to obtain high resolution details from these low resolution images that were obtained. And it's all part of a family of time multiplexing methods, because you're averaging over frames that were acquired during some integration time, or many frames, different frames in different orientations of your illumination, and then you average or perform some post-processing on these results. All of these time multiplexing methods require, first of all, knowledge of the illuminating pattern, because you need it for post-processing. So they are not suitable for real-time imaging, and we wanted to solve this problem. So we propose a new super resolution time multiplexing imaging method, which does not require knowledge of the illuminating pattern and also does not require any post-processing. We get the super resolved image in real time. So the scheme is rather simple. You have a CW laser. It illuminates a rotating diffuser, generating speckle patterns. And then that speckle pattern is splitted on a beam splitter. One part goes to our object, which is a resolution target, and imaged by a low numerical aperture lens or low resolution imaging system onto the camera. The other arm is just a reference arm taking the illuminating speckle pattern directly to the camera. So basically you have on the camera an interference of the low resolution image with the illuminating pattern. You also see that we have an inverting element on the object's arm. This is because we want to have, you know, when you have an imaging system, then the image is flipped, but we want to be overlapping with the illuminating pattern. So we have to flip back our image. That can be a corner prism that can do that flipping. What we did was just placing another high resolution imaging system, basically just to do the flip. Okay, but the idea does not require any additional imaging system, just corner prism that will do the flip. Yes.
Why doesn't the lens kill the interference with the reference speckle?
The lens will kill? No, why? Let's look at the theoretical analysis. So if we look at the output of the camera, you have time averaging over the absolute value squared of the low resolution image and the illuminating pattern. The low resolution image is G times psi. G is the object, psi is the illuminating speckle pattern, and it's convolved with H, which is the point spread function of the image. This is what results in the low resolution image. And then we average over it. If we expand these terms, we get first term, which is just a uniform background due to the speckle. We also get a low resolution term, as you would expect. This is basically equivalent to incoherent imaging, this time average term. But the third term, which is the interference term, will be a super resolved term. How can we see that? If we write the convolution of this in this third term explicitly, then you see that the time average will introduce the correlation function of the speckle. And basically what you get is the object convolved with the point spread function times the correlation function of the speckle. So if your correlation, which is basically what we call the speckle size, is very small, then you're not affected by the PSF, by the point spread function, because you're convolving with a almost delta function. Okay, so it answers your question. Okay, great. So we have a super resolved term, but the problem is that we also have this low resolution term in the background. So how can we have real-time super resolved imaging? So basically, we can introduce low transmission in the object's arm. It happens just because we have the low numerical aperture lens has a narrow numerical aperture. That means that the intensity that is collected is low. So we have some transmission which is very low. And then you see that the second term, the low resolution term, goes like t squared. So that will be very negligible for small t. And we are left with a uniform background, just affecting our dynamic range, but not the resolution. And we have the super resolved term. So with that, we can have computation-free, real-time super resolution. Here are some simulation results. You see the original object on the left top side. You see the low resolution image when we just have the low NA imaging system. And you can see our results with the method A, B, C, and D. The difference between these images is the speckle size. So A is the smallest possible speckle size, 2 pixels. And we go up to 3, 4, and 5 pixels. And as the speckle size increases, the resolution decreases. But we still get higher resolution than what we could have just by having the low NA imaging system that we started with. These are simulation results, and we also have experimental results. Here again, you see A and B are the coherent and incoherent illumination images obtained in the system. So you cannot resolve anything in these pictures. But when we have our rotating diffuser and the interference, as you can see in C, you're able to resolve almost all of the details. And D, E, and F, again, we increase the speckle size simply by having free space propagation for the speckle. And as the speckle size increases, the resolution that we obtain decreases as expected. And to convince you that really happens in real time, here is a movie of what we did in the lab. So you saw the speckle pattern, then the low resolution image, and what you see here is the real-time super resolved image. The integration time here is 50 milliseconds. So basically you see 20 frames per second. And you see that this is excellently stable. You just have a video, super resolved images of your object. That's it. Thank you. Exactly 45 minutes. I'm impressed.
Questions? Well, we did ask quite a few questions. during
Yeah.
it.
It is. Maybe questions from home?
Okay, well, let's thank Ariel for his wonderful talk.